Today I'm going to talk about an application. So we've seen by now lots of ways of writing specifications and proofs in Isabelle. So what's it all good for? Certainly a lot of people who do theoretical computer science will talk about the semantics of some programming language, usually not a real one, usually it's a toy one that includes some interesting feature that they are trying to motivate and publish typically in POPL. And it's expected that any such paper will include proofs of its main results. And the problem is these proofs, doing them by hand, is really unimaginably tedious. So if you've done our own second-year operational semantics course or done one elsewhere, you know how gruesome they are. It used to be worse. They used to put these things on the exam and no one ever got them. So luckily, this sort of thing can be done quite easily in Isabelle. So if you remember from your operational semantics course, just about everything can be done using the operational semantics techniques based on giving a set of rules. So things like type checking, even for quite a sophisticated type system. The evaluation of expressions, again, even in the presence of some complicated exception handling mechanism. Execution, even things like concurrency. So it's really a complete solution to the problem of specifying programming languages. And it's nice to know, well, what I'm trying to say here is these, being given by a set of rules, are naturally inductive definitions, all of them. And so clearly you're going to use induction all the time when you prove things. I have here a teeny tiny example which probably is based on something Mike Gordon did in the 1980s, but never mind that, it's just showing you how it works. We will have the problem here that all of our proofs will be trivial. As is so often the case, proofs are either trivial or incomprehensible. So I am erring on the side of trivial so that things will be understandable to us. So here is a slide. Now actually I think we saw this in the first or second lecture, only I didn't explain very much. So what do we see here? The first line defines locations. For some reason, people who do semantics never want to say what locations are. It kind of bugs them. So they always leave it unspecified, but your memory has got lots of locations, and it maps stuff. So these locations are mapped to values. Now you see here we're being incredibly lazy and using natural numbers as the type of everything in the programming language. Now around this time somebody will probably tell you that you need to have dependent types in order to do semantics because the type of the location, the type of the contents depends on the location or something, which is actually not how it works on any real computer. And in fact, there are some rather neat ways that you can represent a value space without either having dependent types or just pretending everything is an integer. But for now, natural numbers will do us fine. You see we have programming language states which map locations to values. Now we're going to do a rather ugly thing here, and this is because I'm going to give you a semantics of commands for our while language. So we'll have while, if, and so on commands. As for expressions, to keep things really simple, we will not have a syntax for expressions at all. So instead, we're going to represent expressions as functions, as you see, AX for meaning arithmetic expression will map states to values, and BX for Boolean expressions will map states to Booleans. And the advantage of that is that now when I define my programming language down below, There are only 5 possibilities for the whole grammar of the language because I got rid of all the expressions. So if you look now at the bottom, that data type, it says, well, a command, that's comma, command can be skip, which of course is a no-op, assign, which is an assignment, and it's you just give it a location and an arithmetic expression. And the idea here, and remember the arithmetic expression is not given syntactically, but by a function that will map a state to a value. So the idea is you map the current state to a value and plug that value into the location. That's what you want it to do. Next, there is a semicolon, which connects two commands to be executed one after the other. The conditional, which is, of course, if then else. Grammarians, by the way, will tell you it should be if then otherwise, but too bad. And finally, while do. And you see, by the way, on the bottom right there, I have given a built-in, I have provided syntax for those things so that we can write a thing that looks like actual code. This might be a little risky for you to do now when you're getting used to things. Certainly it's nice, when you are used to things and know what you're doing. It is very nice to be able to write code in a natural looking syntax and have it automatically parsed into that combination of assigned, semi, etc. But as I say, when you're first getting started, maybe not. It's all in the manual. Okay, we're going to do the semantics of this. If you remember from your semantics course, you have a big step semantics and a small step semantics. Big step semantics is less expressive but much simpler, so I'm going for that. So with a big step semantics, you have configuration, so there I have a pair, skip paired with a state, and the transition it takes us completely to the terminating final state. So skip started in state S, terminates in state S. Assignment started in state S, terminates in a state that has been updated. You can see same state, except remember the colon equals, and I'm sorry, there are 2 occurrences of colon equals there that mean totally different things. The one on the left refers to the assigned constructor of the previous slide. The other one is the function update syntax, which I did show you in an earlier lecture. So it means that the assignment command coupled with state S will terminate in a modified state where X has been replaced. The value for X will be the expression A evaluated in the state S, and otherwise S will be the same as before, that is for the other variables. In other words, it's exactly what it should be if you've seen this kind of semantics definition before. If you've never had a semantics course before, I'm sorry, I can't really cover all that ground. This is for the semicolon, so do you see that C0 semicolon C1 started in a state S. If C0 terminates, again starting in state S and terminating in some intermediate state S double prime, then provided as well C1 terminates started in S double prime, then the whole thing will terminate. So these are absolutely standard rules that you would see in any semantics textbook, except instead of having a syntax for expressions, we are simply calling these functions. So there at the top right we had AS for the value of the arithmetic expression. Down at what you have there with if then else, you have BS as evaluating the Boolean condition in the state S. And so on for while, and that. So that is the set of semantic rules kind of on paper or in theory. How is that going to look in Isabelle? Well, I think it doesn't look bad, he said. So it's an inductive predicate. Now here, if you note there, I've defined a nice syntax, what we call mix-fix syntax, because you've got a lot of delimiters there. So it's got the angle brackets, a comma, the wiggly arrow indicating the transition. By the way, the slash there, so if you want to look really carefully, the slash is formatting information. It's not part of the syntax of the transition symbol. So that is telling the Isabelle pretty printer that it can break a line at that point, so before the wiggly arrow. Of course, when you look at the rules, you see that they have been typed in more or less literally. And here I'm using the syntax that we defined for example, assignment. You see it's colon double equals, because I didn't want to overload a colon equals. I probably couldn't get away with doing that. There, the semicolon rule, the if true and the if false. I hope you can see that they all more or less correspond to what was on the previous slide. Then we do set up a little automation. We saw this in an earlier example. When you have an inductive definition, the rules given there are logically introduction rules. So when you declare them as intro, I used a very old-fashioned syntax. So I used lemmas. You should probably use the word declare instead. It's more natural. It will have the exact same effect here. It will say, those lemmas should be marked as introduction rules. So auto will try to backwards chain using them. Now, as I said before, when I was talking about inductive definitions, a proof by induction is proving a property of every element of the thing you just defined. So in the case of a operational semantics, a proof by induction will typically be a safety property. If you could think back to any operational semantics course you've done in the past, typically there are properties like type preservation, so that execution of a transition cannot change the type of, say, probably anything, or the contents of a location. Funny, I can't remember that. Probably it's the expression evaluation. Sorry about that minor brainwave. The evaluation of an expression, as you go evaluating it, the type of it cannot change. Anyway, that is a safety property. So by safety, I mean it's something that as you keep progressing, step by step by step, that particular property is preserved from one step to the next, and if it also held at the start, it will be preserved right through to the end. So this sort of safety property is very naturally proved by induction on transitions. What I've got on the slide here, though, maybe doesn't look like a safety property to you. So while true, do C for any particular command, cannot terminate is what that's expressing. I suppose in an informal sense, it's a safety property, because if you did set up a loop and it did terminate, it means your computer crashed, and that certainly would be bad. But anyway, how are we going to prove this? Well, you can't prove it as written. The reason is that, perhaps you remember, a formula has to be what we call inductive. That is to say, when you plug it into an induction rule, it needs to give you sub-goals that actually are provable in themselves, that carry from one thing to the next, one step of a transition to the next. This is too specific because it's only talking about while true, do. And of course, in the cases of the induction, we'll talk about other kinds of commands. So this will not do, but it's very easily modified, this formula. So what do we have here? What we do is we make an initial assumption that we have simply a transition, any transition. Now it will match anything. So any command of the form C paired with a state S terminating in S prime. What do we want to show? We want to show that that command cannot have the form of a looping while. So this, it turns out, is provable by induction. And of course, if once we proved that, then the formula above it will follow trivially. So I've just made this claim that it's provable. What happens when we try it? Well, if you look very carefully, I know it's a bit small, but maybe you have your notes in front. You can blow up your screen. All I've done at the top line of the screenshot there is have the exact same formula in Isabelle notation. And then I invoke induction. So of course eval C is the name of the inductive relation that we define. So eval C dot induct will do induction on those transitions. And then we get our sub-goals. We have 7 because there are 7 rules defining the semantics. Now if you look at them, most of them are trivial. So the first goal is to show that skip is not equal to while. Well, yeah, that's true, because this is syntax, right? So, and if you look at the others, they are all things that are not equal to while. So most of those are trivial. Now look at the very bottom. So sub-goal, well, first sub-goal 6 is also trivial, although now we have while not equal to while. Now it's not so obvious here, but there you have while true, and you also have the assumption that your Boolean condition is false. Of course, true is not equal to false, so sub-goal 6 is also trivial. As for the very last one, if you can see here, the conclusion you're trying to prove is identical to one of your induction hypotheses. And that's kind of cool because, after all, our program is a loop. So it's kind of nice that when we do a proof, we see a thing that looks kind of like a loop itself. So you do auto, and it's proved. So, time for Dilbert number 1. Oh, well, it's all over now. Okay. Now, I'm trying to remember whether we teach a thing called rule inversion in our semantics course, or whether it's known by that name. Have any of you heard of the term rule inversion before? Okay, that was one. It's kind of an important thing. It's like if you see a beer bottle in the gutter, you can infer a lot of things from it. So it's very likely that the beer bottle was purchased in a shop. It was full of beer. Somebody drank all the beer and threw it in the gutter. And you can guess all of those things just by looking at it there in the gutter, even though, of course, it's theoretically possible that somebody made a thing, got a bottle from somewhere else, had the label printed on it, and put it there just to fool you. But that's kind of unlikely. So rule inversion in semantics is a little bit like that. It's where you look at a situation and deduce backwards from the minimality of the inductive definition things that must have happened before. And of course, because we're not talking about the real world and beer bottles, we don't have that thing like probably, because we have no probably. It happened. Whatever we're doing, it happened. So, you see, as I said, our inductive definition gives us a set which is minimal, meaning there are no transitions other than the ones that I allowed. So, for example, for skip, the only way that skip with S can terminate in a state is if that state is S. So if we are told that skip and S terminate with S prime, we know intuitively that S equals S prime. So this is our, if you like, our feeling about the inductive definition. Of course, our feelings don't help us at all when we're trying to prove things, as you have discovered already. What about if then else? So if your if then else terminates in a state S prime, there are two possibilities. Either the condition was true, in which case S prime came from executing the then part, or it was false, and then S prime came from the else part. Loads and loads of semantics proofs that you do will do this sort of thing. Typically, this will be a determinacy proof. So again, in a semantics course, you might have had a thing that says the language is deterministic. That is to say, if I evaluate an expression and get a value v, and then if there's another evaluation of the expression that gives us v prime, then v equals v prime. And typically to prove it, you will have set up an induction in which this sort of thing is happening at every step of your proof. Now, in principle, a rule inversion is done by just looking at all the cases of the rule, and so you can basically do case analysis on the allowed transitions, and most of them will be trivial simply by the fact that skip is not equal to if, for example. And finally, when you get to skip itself, you'll see that the only matches with S equals S prime. But that's a lot of work. There is a nice built-in thing in Isabelle that does it for us. This thing called inductive cases. What you do here, so this will generate new theorems for you. So in this case, you see, you can put the name, whatever name you want to call it. I like to call elimination rules with a rule that, with a name that ends with E, but that's just me. Of course, you can call it whatever you want. What have we got on the right-hand side there? Sorry, just to go through my builds. So these will be, it turns out these will be elimination rules as far as the automation is concerned. And you should declare them using elim or possibly elim bang. You don't have to, but if you do, it will help the automation a lot. But the next thing that we need, the most important thing, whoops, sorry, I pressed it twice. Back. Is the pattern. So the idea with inductive cases is that you type in a pattern that you want to detect. So this is your choice. What I have done here is I've written all the obvious forms of transitions, but you can type in any pattern that you feel like. Of course, it has to be syntactically correct. And it will do the case analysis and give you the exact, according to syntactic rules, the exact combination of cases, or really it's a disjunction of cases, that can satisfy the pattern you give. So there I have skip of S transitioning to S prime, and effectively it returns a rule which says that S equals X prime. It's because it has the form of an elimination rule that it has that weird appearance at the bottom there. I didn't go through the ones for things like semicolon and assignment and so on, but they are all going to be the obvious things, like in the case of if I had them on the previous slide. And what that means is that when you do a proof by induction and then call auto, it will do this case analysis, and then it will get rid of all of those complicated patterns. And by the way, this works repeatedly, right? So let's say your if-then-else has a nested if-then-else, and within that, let's say there's some semicolons, and there's some assignments and some skips. It can keep repeating all the way down until all of those larger patterns have been completely eliminated and all you have are the lowest level consequences of them. Okay, that is the semicolon one. So clearly, again intuitively, if a semicolon is C0 semicolon C1 terminates in a state S prime, there must be an intermediate state S double prime so that C0 terminated in that state. And you can see there it comes out of the form of the elimination rule that is there, that is generated automatically for you. And even if you find it incredibly ugly, you're not really meant to look at it. You're just meant to type auto and have it do its stuff. And by the way, I don't think I have slides on it. If you find this really very unspeakable looking, there is an equivalent thing called inductive simps. So instead of giving you these weird looking elimination rules, it gives you rewrite rules that have the same effect. So rewrite rules that will replace, let's say in that example there, this C1 semicolon, C0 semicolon C1 terminating in S prime, replace it by the formula that says there exists S double prime such that blah, 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 blah. And you can rewrite with those instead. Okay, and as I sort of promised you, we can do a determinacy proof. See what this says. So if command paired with initial state S terminates with T, also terminates with U, then the states of T and U must be equal. The basic thing you're always proving in a semantics course, unless of course your language is non-deterministic. And there, if you see the top line of the screenshot has the exact formula from the previous slide in Isabelle notation. We do an induction. Now, you might say I cheated. How did I know? How did I know to use arbitrary U there? I would say it's kind of obvious. So the first formula is going to be used to drive the induction itself. So when we say apply induct, or we could have used the induction method, it will grab that first assumption there given in the lemma statement. The second assumption will be carried over for us to play with. And the thing is, this U will refer to the value with an alternative value for the evaluation of the command C. The trouble is, when we're doing this inside the evaluation, we are going to have multiple things being evaluated, so it's pretty clear that we need U to be universally quantified so that it can cover all these steps inside where there may be multiple sub-expressions being evaluated and still allow us to distinguish between the evaluation of the sub-expressions and the evaluation of the expression C at the top. So anyway, we type in the formula, we do our induction. We're of course doing induction on eval_c.induct, the induction rule that came from the inductor definition. And a lot of these will be trivial. So you see the first one is trivial by rule inversion. And so will a lot of the others. And basically what's going to happen all the way down is that the top level things, because it's the same command, the top level commands are the same, and then given that they are equal, inside we have these, for example, for if, then in the else parts are deterministic by the induction hypothesis, and the result will build up. I cheated slightly. So why didn't I do by auto? And the answer is either auto didn't work at all or it took too long and I didn't like it. This allows me to show you something. So if you have a proof method with a plus sign, it will apply it multiple times. So BLAST, if you can remember, BLAST doesn't do rewriting, only kind of logical reasoning, and it's pretty fast. And it turns out that because I used rule inversion in the form of inductive cases, it worked with BLAST and it does it pretty well. So this is just a two-line proof of determinacy. Yes?
What concretely means multiple times? Does it mean that it will call BLAST until there's an error, or just before there's an error? Or
yeah, it will call BLAST as many times as it can, so at least once. I guess if it returns with an error, then it won't call it anymore. And here, in fact, it will simply return with an error when you've proved all the goals and there's nothing left to prove, and then you call BLAST again, it will in fact return with an error. Hope that's clear. Okay. Moving on. So as you develop operational semantics in a theorem prover, and I suspect most people do because it's really far, far too tedious to do by hand. So going back a bit, that determinacy proof, you know, if you ever done it, you'd be writing pages and pages, and it would be a miracle if you even copied out the induction hypotheses correctly, because it is incredibly easy to make mistakes. So this is where automated theorem proving really shines, or interactive theorem proving. So now to continue, we're going to talk about the notion of semantic equivalence done on a very simple-minded level. So we define the semantic equivalence of two commands according to, we're going to call them equivalent provided they always give you the same outcome for all possible states. So if you can see, the definition of equivalent is for all states S and S prime, the first command maps S to S prime if and only if the second command takes S to S prime. This, I guess, is probably not the only definition of semantic equivalence you could use, but it's the one, it's sufficient for this example. So here I'm showing it's an equivalence relation. So you remember what an equivalence relation is, right? It needs to be reflexive, symmetric, transitive, and those are all trivial to show. And of course, here is a common pattern of uses that you see where you call auto and you give the very definition of the thing that you're interested in as a simplification rule. You shouldn't always do that, of course, because eventually you will you'll have enough high-level properties of semantic equivalence that you maybe will want to stick to those and no longer keep expanding its definition. Okay, a few other things you might want to prove. So typically, if you have a notion of equivalence, it should satisfy so-called congruence properties. So if I say that one command is equivalent to another, so like it says there, if C1 is really equivalent to C1 prime, and C2 is really equivalent to C2 prime, then I should be able to substitute one for the other in a bigger command. So the first thing I'm proving there is that I can substitute within the semicolon. So if I build the semicolon, command combinator, if I can call it that, it doesn't matter whether I use C1 followed by C2 or C1 prime followed by C2 prime because those corresponding respective commands are equivalent. And indeed, we can prove this again with a single call. This time we need force. Remember, auto can sometimes leave things. Now, if you ask, by the way, how do I know whether to use auto, force, or blast? The answer is very simply, try them, right? So auto is a usual thing people will go for. Say, oh, it took too long, or oh, it left stuff unproved. Then you say, well, you can try force. Took too long, maybe. Or maybe, I mean, I suspect fewer people use blast these days, but for a big problem that is pure logic, it's pretty fast. I guess, have we seen by before in Internet? We must have seen it a number of times. Okay. The second example there is kind of the same idea. I've got two pairs of commands that are equivalent. I want to show that if I build an if-then-else using the first of those commands, C1 and C2, it's the same as an if-then-else built with the C1 prime and C2 prime. Again, it's trivial. You will notice, by the way, there are slight differences between using by proof method as opposed to apply proof method done. So it's a bit more elegant when you have a one-line proof to do it using by. Keep going here. This is not a congruence rule anymore. Now we are proving non-trivial semantic equivalence properties. So the one at the top of this slide is the usual recursive unfolding of while you've probably seen before. That is, while B do C is equivalent to having an outer if then else, if B then, and then you do a C semicolon of another while, otherwise skip. Again, proved automatically. I'm sorry, I did tell you all our proofs will be trivial here because the alternative that they are incomprehensible is not really an option. Yes, question or no? Okay. The last one, if Boolean expression then C else C. This you may note is not true of any real programming language because normally the evaluation of B could cause side effects, but there are other things that you could do. In other words, you could, for a more realistic language, it would be something like B semicolon C, I guess. What about this? Okay, this is a kind of question of style. So you've got, as I said, here in fact, this notion of semantic equivalence has a very simple definition in the form of a quantified formula. And it's actually perfectly okay when you have a simple, straightforward definition, simply to unfold it when you need to break it down into smaller parts and just, say it corresponds to this quantified formula, just do it. But if you like the idea of pure natural deduction and not unfolding things but having a kind of high-level proof calculus, it might be nice to define for yourself or introduce for yourself a rule like this. So this is saying, here is a principle of reasoning that says, if I want to show that C is equivalent to C prime, it suffices to show the thing above the line there, that is C and S terminate with S prime, if and only if C and S terminate with, C prime and S terminate with S prime. So if you want to give yourself this sort of high-level proof calculus, you just state it. So you see in the screenshot there, the formula in quotation marks is simply the expression of the inference rule above in Isabelle. So this is, if you like, going back to the logical framework idea of Isabelle. Then that's provable by auto. And actually, I did a thing which I probably should not have done. I'm mostly demonstrating that that could do it. It's this. So that intro bang means that whenever you call automation and it sees C equivalent to C prime as a thing you're trying to prove, it will definitely backchain with that rule and replace it by the thing above the line, that is to say, the if and only if between the two things. So it's useful to know what intro bang does. I should say, though, that in this particular case, it's a bad idea. And the reason is, we've already proved a whole bunch of high-level theorems about equivalence, that it's congruence laws and things of that sort, that it's an equivalence relation. And if you always get rid of the equivalence symbol and replace it by lower-level things, you won't be able to use those things that you derived. So although, intro bang is certainly useful for some things, you should use it for things that you really definitely want to use that rule and when there is no other sensible way of proving the thing that you're proving. You might say, what example could that be? And I could say simply and introduction, so the thing that says to show A and B, show separately A and B, is in fact declared with intro bang. So nearly all the time when you want to prove A conjunction B, you want to prove the two formulas separately. There are rare occasions when, for example, the A and B support each other in induction, where you will not want that to happen, but for that, just don't call auto before you do your induction in that case. I have now an example of proving something using the rule above. So there we have another semantic equivalence. I guess this is a kind of distributive law for if, which again would not work in a real language because we're changing the order in which we evaluate the conditions B1 and B2. I guess it works in a purely functional language. But anyway, this is a semantic equivalence which holds for our language. It's proved using BLAST alone, thanks to the intro bang above it, because BLAST will say, I can backchain with that. That will immediately get rid of the semantic equivalence symbol, and then it will do the rest using pure logic and probably using a rule inversion, in fact, to prove that. So just to finish up, what if you prefer a small step semantics? You'll probably remember small step semantics is needed to handle things like interleaving and concurrency. Well, just type it in. Really, everything is more or less the same. Variable binding is a really crucial issue in anything non-trivial. Now, there is a thing called the nominal package, which is really cool. Nominal here in the case of names. I don't cover it in the course because it's like a whole world, but basically, if you're talking about a programming language that has variable binding in it, then you are involved with the whole business of name clashes, renaming a bound variable, or doing an induction over the structure of a term where you are assuming that the new names of bound variables in sub-expressions do not clash with the names declared above them. So, believe it or not, the nominal package makes all of that really nice, and it allows you to prove theorems involving a syntax with variable binding in it as nicely as you can in a textbook. So if you are going to do something involving semantics, like for a project this year, or something like that, it's worth learning about the nominal package. Yeah, there's a bit of honesty here. all these were one-line proofs, but in real life, it's not going to be like that.